some fields can be ordered, for example, real numbers. And some fields cannot be ordered, for example, complex numbers and all finite fields. But if a field can be ordered, then is this order unique? Let's recall what it means to be an ordered field. A field F is an ordered field if it contains a subset P, such that P is closed with respect to addition, P is closed with respect to multiplication, and for every non-zero element X of the field F, either X or negative X is an element of P. Such a set P is called a positive cone. A total order on the field F is then defined by saying that X is less than Y, if and only if Y minus X is an element of P. A total order on the real numbers can be defined by letting P be the set of all positive numbers. Please check that all properties of the positive cone are satisfied by this set. Let's prove that this is the only possible order on the field of real numbers. Assume that a subset S of the real numbers satisfies the properties of the positive cone. And let X be any positive real number. Then the square root of X is a non-zero real number, and hence either the root of X belongs to S or the negative root of X belongs to S. A positive cone is closed with respect to multiplication. It follows that in the first case, the square of the root of X, which is X, belongs to S. And in the second case, the square of the negative root of X, which is still equal to X, belongs to S. This shows that all positive real numbers belong to S. Therefore, none of the negative real numbers can belong to S. We conclude that S must be equal to the set of all positive numbers. Thus, there is a unique total order on the field of real numbers with the positive cone equal to the set of all positive numbers. Rational numbers also form an ordered field with the positive cone P being given by the set of all positive rational numbers. Rational numbers are a subfield of real numbers, and this total order is naturally inherited from the total order on real numbers. In fact, this ordering is also a unique total order on rational numbers. Assume that a subset S of the rational numbers satisfies the properties of the positive cone. Then either 1 or negative 1 is an S. If negative 1 belongs to S, then its square, which is equal to 1, also belongs to S. This is a contradiction, because a number and its negative cannot both belong to a positive cone. It follows that 1 must belong to S. A positive cone is closed with respect to addition, so all natural numbers belong to S. Let n be any natural number. Then either 1 over n or negative 1 over n belongs to S. If negative 1 over n belongs to S, then its multiple by n also belongs to S, because a positive cone is closed with respect to multiplication. But this is equal to negative 1, and we already know that negative 1 cannot belong to S. This is a contradiction, and we conclude that 1 over n must belong to S. So the reciprocals of all natural numbers belong to S. Any positive rational number R can be represented as a quotient of two natural numbers, say, k and m. But k over m can be represented as k times 1 over m, both of which belong to S. Since a positive cone is closed with respect to multiplication, we conclude that R must belong to S. We prove that every positive rational number belongs to S, and hence none of the negative rational numbers can belong to S. This implies S is equal to P. We conclude that the order on rational numbers is indeed unique. So far, we have observed only unique total orders on fields. But is it possible for a field to have two distinct orders? Consider a field F that consists of numbers of the form a plus b square root of 2, where a and b are rational numbers. This is a subfield of real numbers, and it can be ordered by inheriting the unique order on real numbers. Consider a subset S of the field F, which is defined as follows: a plus b square root of 2 belongs to S, if and only if a minus b square root of 2 is a positive number. We will now show that S satisfies all properties of a positive cone. Let's take two elements from S. Their sum belongs to S, if and only if the following number is positive. We can represent this number as the sum of two numbers. But each of these numbers is positive by our assumption. So, their sum is indeed positive. It follows that the sum of two elements of S is an element of S, and hence S is closed with respect to addition. The product of two elements of S belongs to S, if and only if the following number is positive. We can represent this number as a product of two numbers. Each of these numbers is positive by our assumption. So, their product is positive. It follows that the product of two elements of S is an element of S, and hence S is closed with respect to multiplication. For the last property of a positive cone, first observe that a number from the field F is equal to 0, if and only if both A and B are equal to 0. This is because A and B are rational while the square root of 2 is irrational. If A plus B square root of B is not equal to 0, then A minus B square root of 2 is either positive or negative in light of the observation we just made. In the first case, A plus B square root of 2 is a member of S. In the second case, negative A plus B square root of 2 is positive. So, negative A minus B square root of 2 belongs to S. But this is the same as the negative of A plus B square root of 2. It follows that for every non-zero element of the field F, either the element itself or its negative belongs to S. This completes the proof of the fact that S is a positive cone. We have therefore two positive cones, P and S, in the field F, and they are different, because, for example, 1 minus square root of 2 does not belong to P, yet it does belong to S. Pause the video, if you need to figure out why. We have proved that the field F has two distinct orders.